All right, good morning everyone, and welcome to our Ultra-Hygienic Drainage Solutions webinar. I'm your host, Greg Jackman, the Specification Program Specialist here at Watts. Today's webinar is the next installment in our WattsWorks Engineering webinar series geared specifically for you guys, our engineer, architect, and specifier customers. Jimmy, can you advance the slide? Just to give you guys a little background on the series, we hold several webinars throughout the year that cover a variety of topics. Our presenters are always our in-house technology and product experts, and thanks to our partnership with the American Society of Plumbing Engineers, ASPE, we're able to provide you with 0.1 continuing education unit credit if you stick around for the entire webinar. So after today, our next one will be on October 29th, where we'll be talking about our hydraulics of backflow detector assemblies, types 1 and 2. So if you're interested in registering for that, please keep your eye out for our emails, or you can reach out to me directly at gregory.jackman@wattsware.com, and I can sign you up. Next slide. So with all that being said, I'd like to introduce you to the presenters of today's webinar, Jimmy Hunt, our Business Manager, Development Manager for BLÜCHER Drains at Watts, and Scott Steinler, our Regional Manager at Watts. Jimmy works with food safety and quality engineers to deliver hygienic drainage solutions specific to the needs and challenges of food processing, commercial kitchens, and bacteria mitigation. Scott has served as the Vice President of Membership, Vice President Technical, and is the current Region 4 Director of the National Board of the American Society of Plumbing Engineers. He has also served on the local board of directors for the Los Angeles, Charlotte, and New Orleans chapters of ASPE in various roles. His background includes working in the plumbing industry as a wholesaler, contractor, designer, and manufacturer's representative. Scott's 20 years of experience give him a unique and comprehensive understanding of the industry as a whole. Next slide.
That's an impressive guy.
Very impressive. Yeah, so just during the duration of the presentation today, the phone lines will be muted, but we encourage everyone to submit questions via the chat window. You just hover over the chat icon at the bottom of the WebEx and type in your questions there, and then we'll address them during and after the presentation. So with all that said, let me pass it off to Jimmy to get started.
Well, thank you, Greg. Appreciate it. Good morning, everybody. Thanks for joining us. I'm going to let Scott sort of run the ball. This is his field of expertise, and he's an ASPE Region 4 Director. So, Scott, I'll let you take it away.
Okay, excellent. Thank you. First thing I want to do is thank everybody for taking time out of their day to join us for this presentation. I really appreciate your attendance. I know many of you have seen it before, but there is new content. So I'm looking forward to presenting that to you today. So a little bit about this course. Through the partnership with the American Society of Plumbing Engineers, you are allowed to claim a 0.1 CEU credit for this course. It is not approved for PDHs for PEs unless your state's requirement allows that. CPDs and CPDTs can use this course towards their recertification. The course may or may not be acceptable for PE renewal. I know North Carolina is a little sketchy about that, so you may wish to check the requirements if you're calling it from there. And as a reminder, just please check with your state to find out if you are eligible for PE renewal or PDH credits. Those are case-by-case basis. So our objectives today, I'm hoping that by the end of the presentation, you're going to be able to list the major causes and consequences of food contamination, identify the primary considerations when selecting drainage for a particular application, analyze and evaluate the performance of drainage materials, describe the unique advantages and benefits of the stainless steel push-fit drainage system, and be able to compare the cost-effectiveness of cast iron and stainless steel drainage solutions. Go ahead and advance, Jimmy. Jimmy, you want to take this one? This is kind of your baby right here, but I'll be happy to discuss it if you'd like.
Yeah, I think the overall message here is we're talking about hygienic drainage, right? We're not talking about storm drains. We're not talking about standard commercial applications, but rather something that really affects all of us. Everybody on this call is impacted by the subject. And what we've learned over our time in research is that food contamination is a serious problem. Food contamination affects everybody. 1 in 6 Americans get affected by some kind of food bacteria, food recall, and hundreds of thousands of people are being hospitalized, and thousands of people die because of bacteria in our foods. And what we're going to talk about today is what that is, where it's coming from, and how we mitigate the risk. Everybody on the call either knows someone or has been affected by food poisoning, bacteria in our food, or some other circumstance. And so it's a problem that kind of affects everybody. So we're going to discuss what that is and how we can prevent it.
And if you don't mind backing up, let's take a look at the bottom line on the previous slide. There is a Food Safety Modernization Act, or FSMA, which is now being enforced, which was designed to improve safety through the food chain by preventing contamination. So the Food Safety Modernization Act applies to every stage of the processing and packaging of any of the foods that are consumed by Americans. The problem with the Food Safety Modernization Act, and I tasked everybody on this call with this, was a lack of involvement from the plumbing engineering community. They have several policies and procedures in place and suggestions that just are counterintuitive to what we know provides good sanitation. So I would encourage everybody to try to get involved on the legislative level to participate in these types of things to make sure that our profession is well represented. Go ahead and advance, Jimmy.
And I'd like to just add that I believe everyone on the call, we're not going to name names, but everyone can think of a recent food recall in the news. Maybe there's a brand that you think of that maybe you think twice about buying that particular product because of something you've heard about. So it's a societal, systemic problem that we'd like to address.
Okay, so there's several codes and authorities that have their kind of hands in the cookie jar here. NSF, which we carry the NSF 14159-3A, which is a very stringent requirement for the design of meat and poultry processing equipment. There's HACCP plans in place at most of the food processing facilities. The UPC has taken this, the IPC as well. We already touched on the Food Safety Modernization Act. Pipes and fittings and drains, you have to comply with the ASME A112.3.1 and ASME A112.6.3. And then we have the ISO 9001. Now, the ISO 9001, in my previous life, I didn't think was a big deal, but that really has to do with continuity of manufacturing. And an example of that would be a particular manufacturer of a type of pipe where, upon closer examination, the outer diameters have variance in them, so they would not connect to the drains properly. So you really are looking for a certain level of continuity when you're dealing with a product. So look for that ISO 9001 wherever it's applicable. Go ahead, Jimmy. Okay, so looking at this chart, you can see that the two leading causes of food recall by the FDA are due to allergen or microbiological contaminants. Now, when we're talking about allergens, that could be something as simple as a undeclared peanut oil or undeclared dairy product in the packaged food. Microbiological is a far more serious problem, so we're going to go ahead and advance and talk a little bit more about that.
But before we do, we have our first poll question, one of 5 poll questions that Greg is going to conduct in the WebEx.
Yes, I'm pulling it up right now.
Great. So the question is, what is the leading cause of food recall in the United States? Your options are foreign material contamination, allergens, microbiological contamination, or process deviation.
Oh, I got the vote. That's cool.
Hopefully you're right.
No, I guessed wrong. I wanted to skew the results.
Okay, we'll give it about 5 more seconds. All right. Greg, do you want to share the results?
Yep. Close the poll here. The WebEx is just giving it a few more seconds.
No worries.
All right, I'm going to share the results now. Okay, there you go.
All right. So The answer is C, microbiological contamination. So 40% of you who answered correctly, thank you very much. That is, in fact, the answer.
Excellent. So 34 of you have just won a dream date with Jimmy Hunt. Congratulations and well done. Okay, so let's talk a little bit about this slide. You're moving on. So let's talk a little bit about this slide. So what we're dealing with here is what is known as WGS in the industry, or whole genome sequencing. I don't know how many people watch the true crime shows at their house, but what they've been able to do is really come up with the technology to isolate and identify the source of food contamination. So let's say you get sick with some sort of food poisoning, you go into the hospital, a sample is taken, and they detect a pathogen in you. They then run an RNA sequence on it if it's a virus, or DNA sequence if it's a bacteria. And then they are able to take swab, and that gets entered into a database. And then there's FDA inspectors and USDA inspectors out in the field that are taking swabs of different facilities. And if they come up with a positive, those are identified, and those are also sequenced in the same way and entered in the same database. So what's happening is they're able now to compare the genomic sequences from these food outbreaks. And what we're finding out is they're able to isolate. So Jimmy in Atlanta gets sick from something, and it actually turns out to be a plant in California. They're able to isolate the source, go back, and then take action accordingly to make sure that that situation is dealt with. So there's really an incredible amount of science and effort going into isolating and making sure that the public is protected. Go ahead and advance. Okay. So what we're looking at now are the FDA food recalls, which are limited to food, tobacco, medical products, and things of that type. You can see that Listeria in 2018 is still the leading cause of recall through the FDA. The numbers have dropped significantly since 2017. You can see that the number there was 600. And you can see that they've really gone down from 2014, 855, 2015, 647, 2016, 785, 2017, 600, and 2018, 355. And that really has to do with the instant identification and isolation of what's been going on in the field. And also, I would say it's a direct result of the HACCP plans, the hazard analysis and critical control points. They're really getting to the point now where we're able to isolate where these things are coming from, what areas need to be cleaned, and what needs attention. Let's go on to the USDA recall and see what they're coming up with.
And I think it's important to note that most common when people think about food bacteria, they think Salmonella and E. coli, which are obviously problems. And with the FDA, it was slightly higher than Listeria, but Listeria is the leading cause in most microbiological recall.
Well, if you look at the USDA, I mean, you could say it's even more dramatic. And this is your commercial food supply. So this is your meat and poultry processing. This is your lettuce. We all know about the romaine scare that happened last year. There was a brand of cheese that was made out in California that killed a bunch of people from Listeria. And you can see that those numbers are going up. So the reason those numbers are going up is because, again, of the advanced technology in the instant detection and isolation of the source of contamination. So if you get a positive swab for Listeria, they're pretty much going to shut you down and you're going to have to deal with it. And as you recall way back on the first slide, if you're talking a major producer, there have been cases where food recalls have cost in excess of $99 million. That's about 5% of all recalls. Now, that's one heck of a hit for a company to take, and that's how serious the USDA is taking this. Go ahead and advance this if you don't mind. So looking at this picture, we're looking at hygienic design for sanitary applications. So these are beautiful kitchen areas and food prep areas. I mean, you've got the guy up in the upper right-hand corner with this beautiful stainless steel tilt kettle going into a nice channel drain. You can see all the workers are gloved up and wearing smocks and stainless steel and plastic conveyors. nice epoxy floors, steam cleaning, steam pressure cleaning. So there's a lot of stainless steel in the kitchen area. So the problem is that when we do this as plumbing designers, and I did this for a very, very long time, is that most of the consideration is what you can see. It's what you can't see that's the problem. Go ahead and advance, Jimmy, if you don't mind.
Right. And as we think about this, where is this bacteria coming from? And obviously it's getting onto the food, but in a lot of studies, the root source analysis shows that the origin of the bacteria is coming from the drain. Go ahead, Scott.
Okay. So again, but to reiterate that point, the most common harborage site for Listeria is in fact the drainage system. Cleaning and sanitation programs tend to focus on the obvious food contact areas. So that's when we were talking about FSMA. If you can't see it, it's really hard to clean it. Listeria present in the drains can easily reach food and food contact areas. So what that means is you're basically translocating the source of the bacteria from one place to another. Now, how do you do that? Well, you could do it with a rolling food cart. Way back on that hygienic slide, you saw a guy using a nice high-pressure steamer to clean the floor areas. But when you do that, you cause particles to basically spread throughout the facility, and that can get on a conveyor. And if that conveyor is going through walls, you can carry it into a different part of the facility. It can actually get into the building insulation itself.
So when you think about following protocol, if you have bacteria in the drainage system that you can't see, it's gone on the floor and then it gets into the drain and it's not cleaned properly, or it's the wrong kind of design, that bacteria will thrive inside warm or dark spaces. And then you follow a cleaning protocol and spray it out, and then to Scott's point, it becomes aerosol. It gets everywhere. It gets on our food. It gets in the air, et cetera.
Well, even to elaborate on that more, it doesn't necessarily need to be a warm area. What Listeria needs to thrive is the same thing all of us need to thrive. We need food, and we need water, and we need a place to live. And that's what the drainage system provides for it. So we know that the traditional drain cleaning practices of using high-pressure steam or a high-pressure hose, they're very, very labor-intensive, and it creates an ideal breeding and spreading ground for the Listeria. Go ahead and advance me again if you don't mind.
Yeah, that gets us to our next poll question. Hopefully you're paying attention. Where do cleaning and sanitation tend to focus on in the typical food production and preparation areas? The answers are sinks, countertops, floors, or all of the above. Where are these cleaning and sanitation people focusing in the typical food production and preparation area?
Okay. Poll is open now. You should be able to see it on the right of your WebEx. Give it another 10 seconds.
Yeah, and thinking about this question, we discussed the FSMA, Food Safety Modernization Act, and its focus on everything but the drainage. Okay. Scott, do you want to speak to the answer here?
The answer is D, all of the above. Obvious surface contact areas are where cleaning and sanitation tend to focus. They don't really focus on what's underneath the floor. So the correct answer would be D. Let's see what the
results should be up now.
Excellent.
Yep, the results
Well
are
done.
in. Most people guessed D. Good job. Must be doing something right, Scott.
That's a first, so I'm very pleased with myself. Okay, so how does this happen? What are we talking about here? So when we're talking about the spread of microbiological agents through a drainage system, and even through a supply system, water supply system, what needs to happen? So we talked about a place to live. So a place to live would be biofilm. So what we end up with are bacterial cells that live in the drainage system. They adhere themselves to the wall of the piping system or into the small spaces. they form a slime layer, and in some cases these layers can be millions of layers thick because there's just so much bacteria in there. But, you're talking on the microbiological level, so it doesn't appear large, but it can be up to millions of layers thick. And then what happens is it becomes antibiotic resistant. So how does it spread? What's happening in the piping system? We'll talk about that on the next slide. Go ahead. Okay, so what we're talking about is what's happening in the piping system and what type of pipe is really propagating this biofilm formation. I do want to preface this by saying that there are other piping systems out there, such as polypropylene and polyethylene. I am working with Watts and some other vendors on trying to get a little bit more data on this to figure out where they fall on the scale in terms of porosity and surface roughness. I used to think that it just really, the coefficient of friction or the surface roughness had most of what was leading to this condition, and I found out that that's not necessarily true. That coefficient of friction isn't always applicable. If you look at a pipe like PVC, which is a great pipe for certain items, but it rates very poorly in terms of biofilm formation because it is a very, very porous material. Second to that, you have asbestos cement and cast iron. Rating somewhere about there is galvanized steel, and then we know that stainless steel 3/16 in particular rates excellent in terms of the resistance to biofilm formation. And that has to do a lot with the metallurgy and the fact that it just does not like to grow. Biofilm does not like to grow on stainless steel. Can it grow there? Absolutely. If you don't clean anything long enough, you can be subject to problems. But just from a material standpoint, it's just not a very, very hospitable environment for it, which is why it's used. There's
what
a scale
was
at the bottom here.
surprising to us is that counterintuitively, plastics, PVC, CPVC are among the most porous drainage environments. And we see it more and more often, even in food production, where CPVC and PVC are the design solution. But to reiterate the point, it's very porous, and biofilms form in porous environments, and that's where that bacteria thrives.
I think on the next slide, we have a blow-up of that graph that's on the bottom of this page. Can you advance one slide, please? There we go. Okay, so what are we talking about here? We're talking about the growth of molecular organisms in welds and or crevices. So the rating scale is millinewtons per meter. So if you're looking at a weld seam or a pore in this case, you can see the water penetrates to 72 millinewtons per meter. Milk penetrates deeper than that at 52 millinewtons per meter. Beer, which I'm recommending beer as a cleansing agent, just not in this, but beer is penetrating to 43 millinewtons per meter. Quartz, which is a cleaning agent, gets down to 24 to 34, which is not enough to penetrate deep enough to reach the soil microorganisms. And the source for this is the EATDG. Jimmy, what does that acronym stand for? That's the European Health something. Are you familiar with that one? It was a seminar that Mark Hayden went to. But basically what it shows is that the cleaning agents are not getting deep enough penetration to kill these soil microorganisms. So just because you foam, just because you cleanse the pipe or try to disinfect the pipe does not mean you're actually taking care of the issue. Let's go ahead and advance. All right. Unfortunately, this was a three-part click, but we've already clicked through it. For those of you that are in the healthcare environment, we're not talking purely commercial kitchen at this point or food processing. There's another phenomenon occurring in the healthcare environment. So if you take a look at this, what you're seeing is the piping underneath the sinks or underneath the lab with all the bacteria spread in it. And we know that P-traps are, although they're code and although they are what we use in the United States, they're filthy. They're absolutely filthy. They retain liquid, they retain waste, despite your best flushing efforts. So what happens is you start getting microbiological blooms either in the P-trap itself or in the piping system. Recent studies have shown that there is an expansion rate of about 4 millimeters per day on that, which means that that bacterial colony is actually propagating and spreading throughout the piping system, and it can literally start in one area. And this is what we're talking about in healthcare. This study was sent to me yesterday, and it came out of Europe, and it says that only 4% of the hand sinks that are provided in the healthcare environment, in the clinical environment, are actually used for washing your hands. So what's going on? What are they being used for? Well, they're dumping biological waste down those sinks, although they're not supposed to. They're dumping leftover food, and what you're doing is you're providing nutrients for that. Hit advance, Jimmy. I want to see if it does what it's supposed to do here. Nope, go back. Okay. Unfortunately, this slide was interactive, but it's not functioning properly. So when you turn on the lavatory, what happens is you splash the water down into the drain, which then causes an ejection of the microbiological organisms to contact surfaces, and it gets spread throughout the facility. So the healthcare environment is really, really, really starting to take a look at what's going on there. And I know that we had
a question come through. Isn't that a double trap on that slide? It may have been a previous slide.
Where's the double trap? I can see a double trap. It's not, graphically, this is not correct. But no, there's only a single, no, they're kind of showing it going, yes, it is. My goodness, you're right. Good eye. So you can see where the T-junction is underneath the center sink, where the piping is supposedly connecting in through the sinks on the right and left. They do have a P-trap on them, and then they're shown connecting in the wrong place, which is above the P-trap on the center one. So yes, that is double trapping. That is forbidden by code. Don't design your buildings this way, but for
the test.
All intents and purposes, what we're showing is, in fact, bacterial spread, and we will get this fixed. Thank you very much for pointing that out. I appreciate that. Okay, so when you're selecting drainage for your application, what are your primary areas to consider? Corrosion resistance, you always want to check your chemical compatibility. There's some things that just are not suitable for certain types of systems. A good example of what's not good for a 3/16 stainless steel system are chlorides. There was a guy from another company that actually pointed this out to us, and he was talking about the granular structure of stainless steel. And he said it's like when you used to go on a road trip and you would put a push pin into the map, and then you would connect the push pin with a piece of yarn or thread or whatever to kind of show your path. And that's how the granular structure of stainless steel is. And what chlorides do is they get deep into that granular structure, and then they follow that roadmap and they tear the pipe to shreds. So always check your chemical compatibility. If you're using if you're using, a plastic, a iron, a steel, just do your due diligence and make sure that you do get that chemical list from the client, which I know can be a daunting task in some cases, but I would advise it. I can tell you that poured-in-place concrete is absolutely the least viable alternative due to lack of corrosion resistance. You can epoxy line those. However, I was just in a facility 2 weeks ago where they had done just that, and that epoxy had peeled off, so that concrete then acts as a sponge. You want to look at heat and temperature because we know that thermal expansion can damage your flooring systems, and you want to look at your load ratings. Frames are necessary where heavy equipment or machinery is used, and I will let you know that hindsight is 20/20. Jimmy, there's a little arrow on that.
Yeah, I tried to play it, but it's just for everybody's benefit. So we hear a lot that these drains that are going into place will not see forklift activity or anything else, and it's foot traffic only. And that may be the case once the building is built and all the equipment is set, but those drains have to be in before everything else. And you can see in the picture, we can't play it, but you can see a forklift with a massive tank going over a foot traffic drain.
It's directly over the top of it. It's like,
Right.
the video's hilarious because it plays in a loop and it's just this forklift going right back and forwards directly over a foot traffic drain. And then you wonder why it doesn't work. Go ahead and advance. Okay, so most of us know what corrosion is, but it is defined as an attack on a material due to chemical or electrochemical reaction within the surrounding medium. When you extract iron ore and other metals from your natural environment and you refine them, they're changed from a chemically stable form to their elemental form, which is not stable. If the metals react spontaneously and change into another state, then that's when it's said to become thermodynamically unstable. And under these conditions, some metals will become surface coated with a thin oxide film, which will help separate the metal from its surrounding medium. And what we're talking about here is iron oxide in the case of stainless. So then when that happens, it's in a passive condition, the material is passivated, the corrosion resistance is considerably improved. What we're looking at here is cast. The passivity of cast is relatively small. It does develop an oxide film, which is rust, but unfortunately that accelerates corrosion by forming more iron oxide, which is being extracted from the pipe. So what you're looking for is an alloy with a chromium content of 12 to 13% or more. These are highly passivated and will not rust in ordinary air and fresh water. Go ahead and advance. Okay, so here's some good examples of what we're talking about. I wish I could see the Q&A panel because I'd like to know if anybody could identify what we're looking at on that far left-hand slide here. It's that vertical pipe with that kind of offset crack running down the center of it. But I guess I'm not going to be able to see that. I was just hoping I would be able to. But these are all examples of, okay, but these are all forms of some form of corrosion occurring within that system. But that one is indicative of one thing in particular. But you could see even the slide on the far right that pipe has basically fallen apart at the floor penetration. Go ahead and advance, Jim. Oh, man, this one I love, but it's not active. Okay, so what are we talking about here? This is a example of corrosion in cast iron. So what happens is, and in particular, and I do want to mention this because there's a lot of engineers on the call, there's an Appendix M that's being proposed in the Uniform Plumbing Code. So that has to do with the reduction and further reduction of the water consumption of plumbing fixtures. So what happens when you do that? So the plumbing code tells you that you need to size the pipe according to a fixture unit chart. Well, the fixture unit chart was based on higher flow fixtures. So if you have a pipe and you reduce the amount of liquid flowing through it, what happens is that media slows down and you end up with a deposit of solids on the bottom of the piping system because you don't have adequate velocity. So there's this very smart man, who's long dead, Manning. He came up with a formula known as Manning's formula. And what Manning told us is what we are looking for is a minimum of 2 to 2.5 feet per second in a piping system in order to keep the suspended solids in the medium when it's passing through the piping system. In this case, we're not achieving that velocity, so we have a deposit of solids. We then get an anaerobic process with bacteria where they're eating these solids and decomposing these solids, which off-gases hydrogen sulfide. I know probably most of us have done some field work, and you know what a dry P-trap smells like, which is why there's trap primers and other interesting things out there in the market to try to keep water, that 2-inch standing water, to try to keep this hydrogen sulfide from entering your building. Hydrogen sulfide doesn't only stink, it is a lethal gas. So if you are in a confined area with hydrogen sulfide, it can literally paralyze your lungs. So imagine that you have a piping system that's breached and you're working in a confined area for an extended period of time with this condition, it can actually be fatal. Anyway, that hydrogen sulfide being lighter than air rises to the top of the piping system, and it condenses and forms sulfuric acid. So that sulfuric acid then coats the inside of the pipe, hits the top level of the liquid or water or whatever's in there, but having a very low specific gravity, it sits on top. And if you don't have adequate flow, you end up with a longitudinal splitting in your piping system because that sulfuric acid is eating away at the interior of your pipe. Go ahead and advance, Jim.
That actually brings us to our next poll question. And you saw a lot of the pictures in the previous slides of that longitudinal splitting shown. And then, of course, there's microbiologically induced corrosion as well, which we can speak to. But this question is, what formula pertains to the flow of liquids in a sanitary waste system? Your answers are Hayes and Williams, Darcy-Weisbach, or Manning's equation.
Oh, we spelled it wrong.
Give it another few seconds. Well, Scott, you're doing a heck of a job because it seems like everybody got the right answer. That's answer C, Manning's equation or Manning's formula.
Manning's equitation?
Yes, equitation.
Excellent.
Thank you for pointing out all of the flaws in this presentation. Well done.
Somebody's got to do it. I'm glad I was able to fulfill that role for you. All right, so here's some vacation pictures that I like to take because I'm basically a boring plumbing engineer by nature. This was at a casino in Vegas, and I heard a tremendous amount of noise coming from one of the lower restrooms. So I decided to walk in there and introduce myself and pretend I belonged on the job site and see what the heck was going on in there. And this is what was going on in there. And this is in one of the new towers. So this condition occurred in just a few years. But you can see that the piping systems have been corroded, obviously. We have some mick going in the lower right-hand corner. This looks mostly like mick to me. If there's a cast iron guy on there, send me an email and let me know what you think this is. I always like hearing from you guys. But what I did is there's that little fitting in the lower left-hand corner. Looks like a little 2-inch combi. And I took my finger and I went up and flicked the fitting and it broke just from the pressure of my finger. So the pipes become very, very thin and very, very brittle, and you can see the iron oxide coating on the inside or rust, but it really accelerated this process, and that piping system decomposed right out of the wall. And again, I want you to understand, and I want everybody on this call to understand that I am not criticizing the cast iron industry. Cast iron has been a reliable, good source of plumbing waste for quite some time. I always tell people, if you want to use cast iron, if you want to use a hybrid system, let's say you're doing a commercial kitchen and you're connecting to a bunch of lavatories or restrooms outside of that area, that's fine. That's what you do. But what I would challenge you with is actually doing the math that's involved in making sure that Manning's requirements are being met. Because if you do maintain velocity in a standard sanitary system, you should not see this condition. The problem is underflow, and the problem is this microbiological contamination. And I don't know what can be done about that other than occasional cleaning. But again, I do want people to understand that I'm not saying that not to use anything. I'm not saying not to use plastics. Everything has a time and place. Just make sure that you're using it for its correct application. In this case, what we're talking about is ultra-hygienic applications. So you need to keep the bacteria out of the drainage system. So I just wanted to stress that. If there's anybody on the line that's with another company or represents another piping system, you guys are great. We love you. We like to use you in the right place. So that's the entire point I'm trying to make here. So let's look at some continual use temperatures. You can see that like PVDF goes up to 285 degrees. Stainless is showing 212, and that's really limited by gasketing materials because stainless, the melting point on that's a lot higher. But this is just a graphical representation of most of the continual use temperatures. In particular, you look at like plastic, and it's 140 degrees. The other big point we want to make is the thermal expansion rate in trench drain materials. So one of the things I want to point out is we see a lot of thermoplastics in breweries and other areas like that. The problem with that is you're setting a thermoplastic generally into a concrete floor. So let's take a look at like HDPE, high density polyethylene. You can see that that has a very, very high level of thermal expansion. The breweries will tell you, no, we're not going to put anything hotter than 120 down there. I'm telling you that's not true. Being in plenty of breweries, they do get shocked with a lot of hot and a lot of cold water. But what we're looking at on this slide in particular, if you look at the difference in the rate of thermal expansion between concrete and high-density polyethylene, this is illustrating that there's a constant push-pull on the system. So we talked a little bit about the poured-in-place concrete trenches and why those aren't a good idea. Well, we mentioned the epoxy lining. So what happens if you have dissimilar materials in direct contact with each other, even trying to be adhesive to each other, and you have a different rate of thermal expansion? There's going to be separation. So that's what I'm attempting to show on this slide, and that's what I hope you take away from this.
And the significance is what we're trying to do is avoid standing water, where we talked about bacteria needs the right temperature and water, and you get life, right? So we're trying to avoid any separation between the flooring and the drainage so that that bacteria can't harbor between the drain and the floor, or worse, underneath the drain, where you just can't clean it. So that's what this slide is representing. I'm going to skip past that question real quick and move on. So this is some examples of, okay, yes, sir.
I'm sorry to interrupt. We had a question come through on that last slide. Is cast iron on the list?
Let's back up and see. No, but my understanding is cast iron has a fairly low rate of thermal expansion. My handbook's downstairs, so I can't pull that data up instantaneously. If somebody would like to email me, I can get them that information because I do have it. But my understanding is that cast iron has a fairly low rate of thermal expansion and contraction. But we're not talking about piping. We're talking specifically trench drain materials in this case. But I would be happy to relay that information to them.
Yeah, and we should probably add it. And typically we're not seeing cast iron trench drains in a hygienic environment. And we've already talked about the corrosive nature of cast iron and et cetera. So these are some examples where there's been thermal expansion between two dissimilar metals. And what you'll see in the picture on the left is between fluctuations in temperature and weight loads, the drain and the floor have become independent of each other, and you've got a full perimeter of separation and gaps for bacteria to flow. You'll also notice when you have a sharp angle, like a 90-degree corner, you're going to find that that's the most likely place to have a stress crack. And stress cracks are virtually uncleanable. They're very difficult to clean. So you'll want to avoid squares as much as possible, or rectangles, because that sharp angle will create separation and a stress crack. You can see on the picture in the middle where there's been deflection on the end of the trench drain due to weight, separation, and thermal expansion. So now all that liquid bacteria will get between the drain and the floor and ultimately underneath. And then on the right-hand side as well, you can see that corner. There's a stress crack directly in that corner of that trench due to thermal expansion. And you'll notice in all these pictures that the resinous flooring that was put on top of the concrete, which is a sponge, that top coat has been eroded away because of the separation between the two systems. Water's going to find a way, and it starts to erode the flooring and chip away. So these pictures you can see where originally there was a resinous floor, and now it's gone or in the process of being gone. So now you've exposed this sponge concrete, which is a massive harborage site for bacteria.
Okay, if you could go back a slide, Jimmy.
Sure.
Go back to the original slide. And I'm going to up the ante here. The first person that is not a Watts employee, the first person that can email me and let me know what the code violation is here, I will give you a $50 gift card to the store of your choice. So take a look. Wow. I'll give you 2 more seconds, and then we'll advance.
I have to approve your expenses, Scott, so it's coming out of your own pocket.
No, I was actually going to put it on your card. I took the liberty of swiping it. So here's a little bit more example of what we're talking about that Jimmy was just mentioning. If you take a look at the top left, that brewery was only a year old when we took this picture. So you can see how that flooring has kind of separated. Again, the one directly below that, you're seeing the cracking in the 90-degree angles. And then there's the one to the right, which is just a hot mess. That's just disgusting, but, we see that a lot. Go ahead. The one on the right here is a very clear separation of the epoxy from the surrounding cast trench. So that goes without saying. And then you can see the oxide film directly on the material itself. So again, we're showing more corrosion. The one on the left, interestingly enough, is Great Divide Brewing. You remember that place, Jimmy, with the little hook game?
Yeah, we promised we wouldn't say names, but it's done now. By the way, Jason.
Oh no, they're fixing it. No. I'm talking to them now. That's why I'm saying their name, because they know it's a problem and they're actually fixing that now. I was just trying to see if you remembered that particular brewery.
I do remember.
All right, we can go ahead and advance. I do.
But before you do, Jason Hawking has answered correctly. The hose in the trench drain is not permitted by code. You need to provide an indirect connection. He's $50 richer.
Who was that? Jason who?
Hawking. All right, moving on.
Okay. So let's talk about load classifications. Do not attempt to read what's on the lower left, because I can't even read that. I'm sitting about 2 inches away from my monitor. What we're looking at here is there's two different standards. There's a DIN standard, which is a European standard. What we need to comply with is the ASME A112.6.3. That is the applicable code in the U.S. And those grades are rated either light duty, medium duty, heavy duty, extra heavy duty, and special duty. So you want to make sure that, and it goes back to that one of the original slides, what traffic is expected over the drain. Pallet jacks will thrash a drain. If you're using a light duty drain and you're rolling pallet jacks over it full of product, you're going to deflect that grate, and you are going to cause bending. So just make sure that you are getting the correct rating, and always look for the correct ASME standard on whatever it is that you're working on.
The point, you have the wrong selection of drainage. You've got heavy-duty things going over it. It cracks. It separates. We saw some examples of that. Then you've exposed your drainage system to open areas, water flowing between the drain and the floor, corrosion, bacteria being created between and underneath the drain.
Okay, so down in Louisiana, they have this little party every year. You can see they invite a couple people to come down, and the place gets very, very full, as you can see. Let's go to the next slide. This is bad. What we're looking at on this particular pipe is what's known as tuberculation. So this is a microbiological problem where you end up with these little bacteria that, and we're talking about that media, remember the suspended solids that sit, this is a grease waste line. So we have all this grease waste and all this food stuff sitting on the bottom of this pipe. So in this case, what happened was that those microbiological contaminants, they basically chewed through the pipe, and they form a stalactite-looking thing. So this is tuberculation. So this particular pipe failed during Mardi Gras. So they had to shut down the entire kitchen of one of the casinos down there, and they lost a lot of money as a result of it. So we were talking about, on the first slide, what's really the problem with contamination or pipe failure? It's not only the cost of the food recall, but it's production downtime. So if you're pumping out product and you lose half of your production time, not a good thing. So again, an ounce of foresight is worth a lot when you're talking about these things. Actually, let's back up. We didn't go over the pros and cons. So what are the pros of using cast iron? High compressive strength, and it is appropriate for many, many applications, as we've talked about, and the low amount of thermal expansion and contraction. The con, it's not good for food processing, sanitation. It does weigh a lot. You will find that it does have higher labor costs to install. It's got corrosion and rust issues. Generally, the appearance subject to microfractures during shipping, and very, very susceptible to biofilm growth. Go ahead, Jimmy. So the cast iron drains, again, there's a lot of pros to them, high compressive strength. They're appropriate for a lot of applications, and they're relatively inexpensive. What we're looking at here, though, is a floor sink that was a cast iron enameled. Now, the problem with this is when these are shipped, occasionally you'll get a possum in them, but not only that, you end up with these microfractures. So if you're dumping condensate or any type of corrosive in there, what will happen is that water will seep through because, as Jimmy already said, water finds a way, and it will seep through those microfractures and then start peeling off the enameling. So the cons here, you can tell that is not ideal for food processing. Same problem with rust. This one, we talked about microfractures, and we talked about the separation from the flooring and susceptible to biofilm growth. Go ahead, Jimmy. I'll let you take plastics.
All right, so we've talked a lot about cast iron. We've talked a lot about different issues and troubles and solutions. And the most common type of solution we're seeing now in food processing kitchens is PVC and CPVC. Now, we already discussed that there are benefits. Obviously, it's very lightweight, it's inexpensive, it doesn't rust, right? So we have that benefit. However, we talked about porosity, and it's an incredibly porous material, therefore susceptible to biofilm formation, which is where that bacteria grows, right? It's also
well, that's only limited to the PVC.
Okay.
CPVC has a different level of porosity, so you could say that definitely applies to PVC. CPVC
Sure.
has its own issues, which, yeah.
All right, so the point is that there is also, because it's plastic, it has temperature limitations. We talked about the continual use temperature of PVC being 140 degrees, and when you're in kitchens, breweries, food processing plants, you will find higher temperatures going down the drain, and the plastics will actually start to soften at 33% of its melting temperature. So what you're seeing here in this picture is from a brewery in the Midwest. That's underneath the flooring, obviously, but what you see has happened, this particular brewery has never seen anything over 180 degrees go down their drain. They measure everything going through, and they've never seen anything more than 180 degrees. But because of the softening, you see that there's little to no flow going through that drain or that piping because it's warped. And so now the liquids start to form on the floor, and you have standing water on the floor and ultimately drainage backup as a result.
Okay.
So we've talked about all the sort of the most common types of drainage, and we see most likely everybody on this call sees either plastics, cast iron, or stainless is the most traditional types of drainage. So what we're talking about specifically is in stainless steel drainage. Stainless steel has the higher use temperatures. It's got less likely to have biofilm formation because of porosity. It's something that is durable and doesn't corrode in most applications. So it's something that you'll spend more money on, but it's something that you'll have peace of mind and understand that it is the ideal sort of long-term solution. It's one thing to pick something less expensive today, but as a very astute engineer once told me, cheap is expensive. So what we're looking for ideally. Go ahead, Scott.
Okay, well, why don't you let me take this, Jimmy, because we've only got about 7 minutes left, and I think we have quite a bit to cover. So the ideal solutions are durable, hygienic, you're looking for easy installation, sustainability, and ROI. So you're looking for that return on investment. So what would a solution that eliminates issues from the past look like? Go ahead and advance. I can't advance the slide. Can you do that? Okay.
I have done.
So here's stainless steel. So this is what an ideal solution would look like. This is a hygienic system, easy to install, and sustainable, and gives you an excellent ROI. Let's go ahead. Okay, so stainless steel piping drains in the U.S. You're looking for 3/16 L below grade, 304 above. The advantages are non-combustible, very resistant to corrosion, hygienic, as we discussed, ROI, long product life expectancy, quick installations, easy maintenance, multiple joint options. There's joint clamps, transition couplings, all kinds of things we can do there. Lightweight, many sizes and custom solutions are available through either us or any of the competitors. and full range of EWV pattern fittings, and sustainability. You can achieve lead points with these. So some of the desired features that you're looking at, we talked about the square corners. You can see that these are rounded corners, so you don't have that thermal cracking. You want to have high-capacity filter baskets because a lot of the processing plants dump a tremendous amount of food waste down there, so you want to be able to intercept that. You're looking for a smooth anti-slip grading, so you're looking for that. Anchor tangs, so when you pour your trench into the concrete, you want to have it grab onto something. So you can push down these anchor tags and then it'll grab on, and that's what you're looking for. So these are some of the desired features, and a high-speed channel design, because that will save you a lot of water. Any debris that falls down into the trench finds its way into a minimal waterway, which enables that thing to flow out much faster. Go ahead. So what are the advantages of push fit versus welded piping? Well, push fit is quick installation. You don't need specialized training on it. They're all prefabricated fittings. Heat expansion and socket, there's no risk of thermal cracking there. Most parts are, well, I could say all parts are leak tested. The biggest difference between a push fit versus a welded piping has to do with how it's welded. So if you're doing factory welds, you use a inert gas inside and outside when you make that weld. And then what you do is you want to passivate that weld in a pickling bath. So the disadvantages of joining, the disadvantages of welded and mechanical joining is it does require skilled labor. And I've seen piping up to 10 and 12 inch diameter. If any of you are welders, just imagine the time necessary to weld on it, to make a joint on a 10-inch pipe. Very, very time consuming. It does require specialized tools. You do have to have two people there, one guy welding, one on fire watch. It's expensive, and it's prone to corrosion when field welded. So why is it prone to corrosion when field welded? The process of welding stainless steel pipe removes the chromium oxide film that we were talking about, the passivation. So unless you have the chance in the field to repassivate that piping, what you are creating is an Achilles heel in the system. So just by the act of joining the pipe and not passivating it, or not allowing it the time to passivate, that's the weak spot. So as to pickling and passivation, you take all welded corners, all welded fittings, and you submerge them in a hydrofluoric and nitric acid solution. If the surface is dirty, what it usually is, with a residue scale, welding slag, the formation of the passivation or the chromium oxide is impeded. So that increases the risk of corrosion. So the acid pickling process, it removes all the impurities from the surface of the steel and helps form that chromium oxide film again. We know that stainless steel has a self-healing property, so when the surface is damaged chemically or mechanically, eventually the oxide film will reform itself if it has time to do so without being further corroded. So here's a good example of savings with a high-speed channel. So this was a particular brewery that we did, and we took a look at it and saw that there was an average savings of 10 minutes per dump cycle at 13 GPM twice a day for 365 days. So we did the math. 10 times 13 is 130 gallons saved per dump twice a day, or 260 gallons per day at 365 days a year. So they saved almost 95,000 gallons per year. So that is an ID point that you could also get through LEED if you want to substantiate your claim, and we can help you fill out that paperwork. We can look at the labor savings as well. Oh, never mind, we could go on, but there were significant labor savings. So what is the cost of a push-fit stainless steel piping system over a traditional cast iron system? And I believe this is a poll, so we'll give you a few minutes.
Yep. This is our last poll of the WebEx. So the question is, what is the cost of a push-fit stainless piping system over a traditional cast iron system? The answers are not up on the screen, but the options are 2 times, 3 times, 4 times, or none of the above.
There you go. It should be up right now.
It's up. So everybody on the call, what is the estimated cost of a push-fit piping system over traditional cast iron? Is it 2 times more, 3 times more, 4 times more, or none of the above? Give it a few more seconds. We've got some astute listeners here. The answer, of course, is none of the above. And we're going to move on and explain the logic behind that statement. Go ahead.
Okay. So what we look at is in a typical territory with a predominant labor rate of $100 or more, a stainless steel piping will cost on average anywhere from 9 to 20% more than a traditional cast iron system. In some cases, this can be significantly less. What I tell people is when they initially call me, always assume a 20% premium, even though it can be less. So here was an interesting job down at the Orleans Parish Prison. You could see that the ratio was 1 to 5 for labor and material. So the cast iron material, I think there's a typo here somewhere. Nope, we're good. Okay.
Go ahead, Scott.
Something's not right here, but there's a typo here. But you can see that the labor total for cast iron was 145, and the labor total for just the push fit was 40,000. So by the time all was said and done, the stainless steel, but keep in mind that the predominant labor rate down there is only $50 an hour, or was at this time. So the material and labor cost was $340,000 in New Orleans and $223,000 if they had used cast iron. Now let's take that to a major market, LA, New York, Chicago, and apply the appropriate labor rate. You could see that there was a 3% difference. If all things being equal, if the only thing that changed was the labor rate, there would have been a 3% difference. And we're talking a 70-year product under standard corrosion conditions versus the relatively short lifespan of cast. Move on. Here was a job that was done up in Northern California. Engineer put this together, and you could see an 8.9% variance on this. So we'll just get past that one. And mainly it has to do with the amount of hangers and supports and the time necessary to make joints. And this is going to be what I believe is our last slide, or second to last slide. And this is what I want to leave all the engineers with, is that you have the ability that if you write a spec, and there is now case law in place. This was written by Steve Noodleman. He's I know whoever gets PME magazine, but Steve writes a lot of legal articles. And what this case basically showed was that there was a company that specified a particular product based upon the performance of that product for the application. The contractor took them to court over it because they wanted to do a value engineering process on this. The engineer did not back down, and the engineer actually won this case because it's the engineer who is accepting the legal liability for the protection of the health, safety, and welfare of the public. So you have the powers. So not all things are created equal. Go ahead and advance. And I hope you learned this stuff. We did very well on the polls, so it looks like everybody did very well. And with that, I will leave it to Jimmy Hunt to close out. And again, I thank you very much for your time and attention, and I'm trying to be as respectful of your time as possible. So, Jimmy, you want to bring us home?
Yeah, thank you very much, Scott. You did a wonderful job. I think you made some very solid points, and hopefully everybody took away these 5 learnings and understand that stainless steel, push-fit stainless steel isn't an all solution for everything, but I think if you take anything away, understand that there are application-specific solutions, especially when you're talking about food process, kitchen, healthcare, sanitary applications. You need to look really seriously at what you select. And with that, Greg Jackman.
Yes, thank you, Jimmy. We did have one question come through on the chat here regarding the last poll. Does that poll question include labor costs?
It does. That's total installed costs of push-fit stainless versus cast iron. It's labor, material. The total difference is between 9 and 20%, depending on location, application, et cetera.
And it is absolutely predicated on labor, because if you just look from a material standpoint, I can safely say that stainless steel push-fit systems in 3/16 are roughly 300% higher in list price than other systems. So that labor is the key to what makes this system affordable and gives you that return on investment. So that is a very good question, and yes, it is absolutely predicated on labor.
Great.
Excellent. Another question that came through here, is cathodic protection for underground stainless steel necessary?
Can you ask that question again?
So is cathodic?
Does it require cathodic protection? The answer is no.
Okay. Okay. Jimmy, can you go up to the previous slide?
Yes, sir.
Just want to show everyone our contact information. So again, I want to thank our presenters, Jimmy and Scott, today, and everyone who joined us, and thanks for hanging in there after the top of the hour here. So just to let you guys know, a recording of the presentation and your CU credit for this webinar will be emailed to you. If you have any logistical type questions, you can send them to me, gregory.jackman@wattsboro.com. Any sort of technical or topic related questions, send them to Jimmy or Scott, and you can see their emails on there as well. And for those who requested a copy of the presentation, I will send it to you. And Jimmy, if you can click to the last slide here. I just wanted to mention, when you guys close down this WebEx, it'll bring you to a page where you can sign up for our next webinar. That's on October 29th on hydronics of backflow detector assemblies, types 1 and 2. You can watch a couple of our BLÜCHER videos, one the Madtree Brewing testimonial, BLÜCHER Hygienic Pro Drains video, our 6 ways the BLÜCHER Hygienic Pro channel saves time, water, and money video. You can take our online CEU course, Choosing Stainless Steel Drains for Caustic Environments. You can also visit our on-demand webinar page, so you can watch all the past recordings of the webinars we've done this year in our series, and you can take quizzes after you watch the webinars to earn more ASPCU credit. So with that, that's it. Thanks again for joining us today, and have a great weekend.
Thanks, everybody. And congratulations, Jason, on your $50 gift card.
Courtesy of Jimmy.
Scott, I emailed you the contact information for Jason, so you can reach out to him.